On another linear programming problem. This time it is a blending scenario. As you have already attempted the question, I shall not read through the details, but I will just point one thing out that may have caused confusion. Brand Y feed. This is per pound. These figures here are the amount of ounces of each ingredient is found in your pound of brand Y feed. So for example, in a pound of brand Z feed, you have 10 ounces of ingredient A, 3 ounces of ingredient B, and 0 ounces of ingredient C. Okay, let's jump straight in. First thing we need to do, as always, what is our objective? Well, from the information we deduce, because it tells us, that we're looking for the lowest cost, and therefore we are trying to minimize that cost. Very simple. Second thing, what is our decision? Well, we're told here how many pounds of each brand at the lowest cost, plus we need to meet this minimum requirement. Okay, that's our decision then. So we're going to detail how many pounds of each brand, Y and Z, to meet the minimum requirements whilst minimizing the cost. Here we also want to detail our decision variables. So what we're trying to do is look at how many pounds of brand Y feed and how many pounds of brand Z feed we shall use. So these will be our decision variables. We have the number of pounds of brand Y feed. We want to detail that as a letter. Now you can choose any letter you want. Usually it's X and Y or A, B and C. But because these letters are already included as types of ingredients or names of brand feed, we should just go with a different letter. We'll go with M. And we have the number of pounds of brand Z feed, and we'll go for a letter T. These letters, the letter T, seen anywhere else in functions, the objective function or the constraints, T will represent the number of pounds of brand Z feed that we have. Step 3, objective function. So how can we detail our decision, our objective, in an algebraic function, in a mathematical formula, which Solver will utilize to give us our optimal solution? Well, have a look at the decision. We're looking at the cost. So if we try and identify the cost, which we can because we are told that it is $0.02 for brand Y feed and $0.03 for brand Z feed. So we're looking at the cost of the number of pounds of brand Y feed and the cost number of pounds of brand Z feed. And this will give us our minimized cost. The optimal solution. So for example, if we were to have 5 pounds of brand Z feed, well, that would be represented by T. T would become 5. Then this in the equation, we'd replace the letter T with a multiplied by 5. And that will give us our solution. Sorry, let me just pop the T back in there to complete. Lovely. Step 4, constraints. These are any constraints, anything that we have to work with, we have to adhere to when we are calculating our optimized solution. Now we do have a couple of constraints in here because we are told there's a monthly minimum requirement that we have to meet in terms of certain ingredients. So for ingredient A, we have to have at least 90 ounces. That 90 ounces are going to come from the mix of brand Y and brand Z feed, because we're going to get 5 ounces for every pound of brand Y and 10 ounces for every pound of brand Z. So let's write this down as a constraint. As a function, this will appear as the number of pounds, the number of ounces that we can get from all the pounds of brand Y we will have. It will be 10 multiplied by T. Now we use the inequality greater than or equal to because we have a minimum threshold that we have to meet. It is greater than or equal to, on the right hand side, 90. We have a minimum requirement of ingredients B, and it's going to be 4m plus 3t. Again, it's going to be greater than or equal to the minimum requirement of 48. And for C, we're looking at 0.5 m plus 0t is greater than or equal to 1.5. It is your choice whether to include this 0t or not. Include it or not, the equation will still be the same. So there are constraints from the given information. What you'll also have with linear programming problems, potentially 2 other constraints, non-negativity constraints and an integer constraint. So first of all, can we have a negative number of pounds of brand Y feed or brand Z feed? Well, no, we cannot. So we shall include our non-negativity constraint, which will show that M and T have to be 0 or above. The other one is integer. So does it detail that the amount of pounds of brand Y or brand Z has to be a whole number? Well, no, it doesn't. So we assume, therefore, that we could have 1.2 pounds or 3.5 pounds. So we shall not include our integer constraint. There are constraints. Now we know that we can move on to solving. To be able to solve it through the use of Excel or Google Sheets, we have to set up the information that we have in steps 1 to 4 into a usable format. So this is the table that we'll always detail. So we start off with our decision variables. This is going to be the amount of pounds of brand Y feed, which would be M, and the amount of pounds of brand Z feed, which would be T. For now, we're just going to put in zeros. And look at the objective function. What we're dealing with is cost. So right below, we're going to include the cost. Respective cost amount per pound. Then we're going to have a look at our constraints. And these will be set up in a way that we have a left-hand side, we have the sign, we have our right-hand side. So I'm just going to be lazy, copy and paste our constraints down here. So for A, we want to turn this function here and represent it in the table below. So we know that we have 5m, we're just taking the number, and 10t. Left-hand side we'll come back to, the sign, greater than or equal to, and the right-hand side, 90. And this left-hand side, we're going to put into a formula representing this left-hand side. So we're going to say equals 5 multiplied by m plus 10 multiplied by t. And that is the left-hand side of the equation. Beautiful. Now, just to make sure that that is working, we change the m for 1. This cell changes to 5. And if we were to change t to 1, we'll hope it to be 10. A presto, it is 10. That formula is working. In requirement of b, we do the same thing. Put our sign, put our right hand side. Now, you can use the function SUMPRODUCT, which returns the sum of products. Select both of these two, comma, select both of these two, enter. It does the same thing as we did in this cell, but it's quicker, more efficient and easier. And then same thing for C, we have 0.5, we have 0, create that equal to 1.5. Now you can copy and paste your sum product, but beware, this blue cells, it is pulled down because we've not fixed it. The way that you fix it is by including a $sign, and this will then fix that, and it will be stagnant, static, wherever you copy and paste it. So we're just going to add in one in here and one in here, and yes, it changes these. These formulas are working well. The final thing we want to do is to include our optimized solution or our objective function, and that is 0.2 multiplied by m, 0.03 multiplied by t, or as seen here, the objective function. Okay, almost ready to go. What we will do, to make it easier to read this table, we're just going to add in some colours. So we'll make the figures that we want solver to change green. We'll make our limiting figures red, and what would change based on the changing variables, we'll make orange. Let's just add in some lines to make it extra neat. And fully bold. Okay, so we are ready to go. So let's open up our solver. So our parameters. Our objective will come from this cell here. Always has to be a formula. Are we trying to maximize, minimize, or to put a value of? Well, we're trying to minimize our cost. Our decision variable cells are the remaining two green. Then we need to add on our constraints. So first off, you're adding the left-hand side. You're changing your quality to the correct one, and then you're adding the right-hand side. And you're clicking OK. A shortcut you can do here when your constraints, if you have a sign that is the same for multiple constraints, well, we can select all of them at the same time. Select these bottom two constraints for ingredients B and C, select our sign, and then our right-hand side, select those two. We click OK. We have our constraints added in, our non-negativity, we'll leave the box ticked, and we'll select the method for simplex. So we are ready to solve. We can see that Solver has found a solution, click OK, and here we have. So our solution is to utilize 8.4 pounds of brown Y, 4.8 pounds of brand Z. And we have the minimized cost, the optimal solution at $0.31. And just to check, yes, our left-hand side is greater than or equal to our right-hand sides based off of our sign. So that is our solution.